NASA's revolutionary nuclear space engine, a game-changer for human Mars missions in 45 days. Date, May 24, 2025. Overview.
NASA is poised to revolutionize space exploration with its development of a nuclear thermal propulsion (NTP) system that could cut travel time for human missions to Mars from approximately 6 months to just 45 days. This innovative technology has undergone successful testing at NASA's Marshall Space Flight Center (MSFC) and is being developed in collaboration with industry partners such as General Atomics Electromagnetic Systems (GAMS) and Space Nuclear Power Corporation (SpaceNukes).
Key developments and testing milestones. 1. Initial tests and collaboration.
In January 2025, NASA conducted critical tests on advanced NTP reactor fuel at MSFC, confirming that the fuel can endure extreme conditions including temperatures exceeding 2,727 degrees Celsius (4,940 degrees Fahrenheit).
This success, a collaborative effort between NASA and GAMS, has included independent validation tests to ensure fuel performance across various environments.
The NTP system is projected to achieve efficiencies 2 to 3 times greater than traditional chemical propulsion methods.
2. Technology overview. NTP systems operate by utilizing a liquid propellant, most likely hydrogen, heated through the fission of uranium within a reactor core. This process produces thrust much more efficiently than conventional chemical rockets, enabling spacecraft to attain significantly higher speeds. The implications of this technology are profound, as it can alleviate risks associated with long-duration space missions, including cosmic radiation exposure and the logistical demands of extensive life support systems. 3. Future Mars missions.
The potential to reduce transit time to Mars significantly addresses critical challenges faced by astronauts, such as limited medical support and the risk of equipment malfunctions during long journeys. Shorter travel times would not only enhance astronaut safety by reducing radiation exposure but also minimize the amount of supplies required for the journey, making human exploration of Mars more feasible.
Common themes across sources. NTP's game-changing potential.
Across all reports, the transformative impact of NTP technology on human space exploration, particularly for Mars missions, is consistently emphasized.
Collaboration with industry. The partnership between NASA and private entities like GAMS and SpaceNukes underscores a collaborative approach to advancing propulsion technology in space exploration. Testing successes.
The successful testing of NTP fuel and reactor technology is highlighted as a significant milestone in the development of operational nuclear propulsion systems.
Differences in perspectives.
While there is consensus on the transformative potential of NTP technology, sources differ in the specifics of testing processes and broader implications.
For instance, one source focuses more on NASA's partnership with SpaceNukes and the development trajectory for nuclear electric propulsion, while another dives deeper into the technical workings of the NTP system and its implications for astronaut safety. Timeline of events.
2018, SpaceNukes successfully designed and tested a 1 kilowatt kilopower reactor for NASA, providing a foundation for future advancements in nuclear propulsion. January 2025, NASA announces successful tests of revolutionary NTP reactor fuel at MSFC, demonstrating its viability for deep space missions. May 2025, SpaceNukes is designated as the industrial partner for developing advanced nuclear electric propulsion systems, aiming for a flight demonstration and further testing.
Conclusion.
The advancements in nuclear thermal propulsion technology represent a pivotal moment in the quest for human exploration of Mars and beyond.
Continued testing and refinement of NTP systems could redefine the possibilities of interplanetary travel,
making the dream of human missions to Mars more achievable than ever before.
NASA's commitment to collaboration with industry partners ensures a multifaceted approach to overcoming the challenges of deep space exploration. Source summaries. 1. Military aerospace. The article discusses how nuclear engine technology supported by NASA could facilitate human travel to Mars in just 45 days, emphasizing the potential for military and civilian applications of nuclear electric propulsion technologies. 2. Daily Galaxy. This source highlights NASA's successful testing of advanced NTP reactor fuel, detailing how the technology could address significant challenges in human Mars missions, including reducing radiation exposure and logistical complexities. 3. MSN News. The report notes the advances in NTP technology and its implications for future space exploration, reaffirming the significance of NASA's work in collaboration with industry partners. Future steps. While the test results are promising, further research and development are needed to refine NTP technology and integrate it into future space missions. NASA plans to continue working with industry partners like GAMS to optimize NTP systems in preparation for operational use. Upcoming projects, including the Artemis program and potential Mars missions in the 2030s, could benefit significantly from NTP technology, which is essential for the long-term vision of expanding human presence in space. As NASA and its partners continue to push the boundaries of propulsion technology, the dream of faster, safer, and more efficient interplanetary travel moves closer to reality. The recent successful testing of NTP fuel marks not only a technical milestone but also a profound step forward in humanity's quest to explore the cosmos. NASA's development of a nuclear thermal propulsion NTP system marks a significant leap in space exploration technology. With the potential to drastically reduce travel time to Mars from approximately 6 months to just 45 days. This advancement, achieved through extensive testing and collaboration with industry partners like General Atomics Electromagnetic Systems (GAMS) and Space Nuclear Power Corporation (SpaceNukes), introduces several counterintuitive aspects worth noting. Counterintuitive aspects of the NTP technology. 1. Safety versus speed. While the primary appeal of NTP technology is its ability to reduce travel time significantly, the speed also presents a paradox regarding astronaut safety. The shorter travel time means less time exposed to cosmic radiation, but it also necessitates higher speed travel, which could introduce new risks associated with rapid acceleration and deceleration. The implications of these factors on the health and safety of astronauts during the journey are complex and require careful consideration. 2. Efficiency through radioactivity. The idea of using nuclear fission for propulsion may seem counterintuitive given the public perception of nuclear technology as dangerous. However, NTP systems promise efficiencies 2 to 3 times greater than conventional chemical rockets. This efficiency stems from the fission process, which, despite its radioactive nature, allows for more energy to be harnessed from a smaller amount of fuel compared to combustion-based systems. This challenges the typical notion that nuclear energy is primarily a liability rather than a viable tool for safe and efficient space travel. 3. Collaborative development versus individual agency. The NTP program showcases an unusual collaboration between government and private sectors, which is often viewed skeptically in terms of efficiency and accountability. Yet the partnership between NASA and entities like GAMS and SpaceNukes is presented as a significant advantage. It suggests that leveraging private sector innovation can drive breakthroughs in technology that might be slower to develop within the confines of government agencies alone. This shifts the narrative about public-private partnerships in aerospace from one of skepticism to one of potential synergetic advantage. 4. Long-term versus short-term goals. The emphasis on immediate advancements in propulsion technology may overshadow the long-term implications for space exploration. Although NTP systems are aimed at reducing travel times and enhancing safety for missions to Mars, they also open new frontiers for exploration of the outer planets and sustainable human habitats. This suggests that while the immediate application focuses on Mars, the broader vision could enable humanity to venture further into the solar system, a goal that may seem distant with current propulsion technologies. 5. Public perception of nuclear power. the notion that nuclear power can be a solution for space travel contradicts widespread public concern about nuclear safety. While many view nuclear technology with apprehension due to historical accidents and environmental concerns, the application of nuclear thermal propulsion in space could redefine its role as a clean and efficient energy source. This juxtaposition raises questions about how society reconciles its fears with the potential benefits of nuclear technology in advancing human exploration of space. 6. Resource allocation and mission logistics. Current missions to Mars must account for the lengthy travel time and the associated resource demands: food, medical supplies, etc. The NTP technology's ability to shorten the journey could paradoxically allow for a more concentrated and efficient use of resources. Yet it may also lead to an underestimation of the logistical challenges posed by faster missions. As missions become shorter, there may be less time for contingencies, requiring astronauts to be better prepared for emergencies, a counterintuitive shift from longer, more predictable missions. 7. Technological optimism versus historical setbacks. The enthusiasm surrounding NTP technology stands in contrast to historical setbacks in nuclear propulsion development, which has faced numerous delays and challenges. The optimistic outlook for this new technology may overlook the complexities and potential for unforeseen issues that have previously hindered nuclear propulsion systems. The contrast between current excitement and past failures emphasizes the unpredictable nature of technological advancement in aerospace. 8. Environmental considerations. While nuclear thermal propulsion is often touted for its efficiency and reduced travel times, the environmental impact of developing and deploying such technology can be nuanced. The production of nuclear fuels and their long-term storage could present environmental challenges that complicate the narrative of clean space travel. This highlights a counterintuitive aspect of the technology. While it may offer immediate benefits for space missions, it could also entail environmental trade-offs that need to be carefully managed. Conclusion. The advancements in NASA's nuclear thermal propulsion technology present a multifaceted view of space exploration that challenges conventional wisdom. The counterintuitive aspects of safety, efficiency, collaboration, public perception, and environmental impact reveal a complex landscape where the promise of faster, safer space travel coexists with inherent challenges and risks. As NASA and its partners continue to refine this technology, the dialogue around nuclear propulsion will need to navigate these complexities to fully realize its potential in human space exploration. In the context of NASA's development of nuclear thermal propulsion (NTP) technology for human Mars missions, several critical elements in the report may be overlooked, yet they hold significant implications for the future of space exploration. Here are some of these key points along with explanations of their significance. 1. Efficiency and speed over conventional systems. The report emphasizes that NTP systems can achieve efficiencies 2 to 3 times greater than traditional chemical propulsion systems. This is not merely a technical detail, it represents a fundamental shift in the capabilities of space travel. The ability to travel to Mars in just 45 days instead of 6 months is monumental. Such efficiency not only reduces the logistical challenges associated with long-duration missions, such as food and life support, but also mitigates the health risks from prolonged exposure to cosmic radiation. Significance: faster travel times could redefine mission architectures, allowing for more ambitious exploration objectives such as establishing human habitats on Mars or conducting extensive scientific research in shorter windows. The implications for astronaut health and safety are profound. Reduced travel times mean shorter exposure to space hazards, potentially leading to lower morbidity rates among astronauts. 2. Collaboration with private industry. The partnership between NASA and private entities like General Atomics Electromagnetic Systems (GAMS) and Space Nuclear Power Corporation (SpaceNukes) is a significant aspect that may be underestimated. This collaboration is not just about sharing resources but is indicative of a broader shift towards leveraging private sector innovation in public space exploration efforts. Significance: engaging private companies can accelerate technological development and reduce costs. It encourages a diversity of thought and innovation that can lead to breakthroughs not typically possible within government structures alone. As the space sector evolves, such partnerships could become a blueprint for future missions, fostering an ecosystem where public and private sectors work synergistically to achieve common goals. 3. Testing conditions and results. The report details the extreme testing conditions that the NTP fuel was subjected to, including temperatures exceeding 2,727 degrees Celsius (4. 940 degrees Fahrenheit and rapid thermal cycling. While these specifications may seem technical, they are integral to validating the fuel's viability for space missions. Significance: the ability of the fuel to withstand such extreme conditions confirms its robustness and reliability for deep space missions. This is crucial because any failure in propulsion systems during a mission could jeopardize the safety of crewed missions. The successful testing results also build confidence in the technology, making it more likely to be adopted for upcoming missions. 4. Addressing astronaut health and safety challenges. The report mentions the various health risks astronauts face during long-duration space missions, such as cosmic radiation exposure, equipment malfunctions, and limited medical support. The NTP technology addresses these risks by significantly shortening transit times to Mars. Significance: this is not just a technical advancement but a crucial step towards ensuring the well-being of astronauts on long missions. Health considerations are paramount for NASA and other space agencies as they work to ensure that space exploration is not only feasible but also safe for human life. The psychological and physical impacts of extended space travel are well documented, hence reducing the time spent in transit directly correlates with better outcomes for crew members. 5. Broader implications for space exploration. While much of the discussion centers on missions to Mars, the potential applications of NTP technology extend beyond the red planet. The report briefly touches on how this propulsion system could facilitate missions to the outer planets and support the establishment of sustainable human habitats on the Moon and Mars. Significance: this suggests a paradigm shift in how humanity might approach space exploration as a whole. With NTP technology, missions that were once considered too ambitious or unfeasible may become possible. The ability to efficiently travel to distant celestial bodies could open new avenues for scientific discovery and human expansion into the solar system, fundamentally changing humanity's relationship with space. 6. Long-term vision for interplanetary travel. The report indicates that NTP systems could support long-term visions of expanding humanity's presence beyond Earth. This notion of a sustainable human presence in space is critical, as it aligns with broader aspirations of becoming a multiplanetary species. Significance: this long-term vision is not just a lofty goal, it has profound implications for humanity's future. As Earth's resources become increasingly strained, the ability to establish self-sustaining colonies on other planets could become essential. The development of technologies like NTP is a step toward making this vision a reality, highlighting the importance of investing in space exploration. 7. Potential for future missions and applications. The ongoing testing and refinement of NTP systems pave the way for future missions, including the Artemis program and potential Mars missions in the 2030s. The report hints at upcoming projects that will utilize this technology, which may be overlooked in the narrative focused on current achievements. Significance: understanding that this technology is not just a theoretical concept but is actively being developed for imminent missions underscores the urgency and importance of current efforts. It emphasizes that the advancements made today will directly impact the missions of tomorrow, making it essential for stakeholders to support continued funding and research. Conclusion. In summary, while the report on NASA's revolutionary nuclear thermal propulsion technology outlines significant advancements, it is the nuanced implications and interconnectedness of these developments that warrant deeper consideration. The efficiency of NTP systems, the collaborative nature of its development, the rigorous testing conditions, and the potential for broader applications all highlight a transformative moment in space exploration. Recognizing these factors is essential for understanding the full impact of NTP technology on the future of human space travel and exploration. 1. Technological breakthrough in propulsion systems. NASA's development of nuclear thermal propulsion (NTP) technology represents a significant advancement in spacecraft propulsion. Traditional chemical propulsion systems require approximately 6 months for a one-way trip to Mars. In contrast, NTP technology could reduce this travel time to just 45 days, effectively transforming the feasibility of human missions to Mars and beyond. The NTP system operates by heating a liquid propellant such as hydrogen using the fission of uranium, which generates thrust more efficiently than chemical rockets. This efficiency not only enhances speed but also has profound implications for the design and execution of long-duration space missions. 2. Addressing astronaut safety and mission logistics. One of the critical advantages of the NTP system is its potential to mitigate many risks associated with extended space travel. Longer transit times increase astronauts' exposure to cosmic radiation and the likelihood of equipment malfunctions, which can compromise mission safety. By significantly reducing the travel duration, NTP technology decreases these risks, allowing for safer missions with fewer logistical challenges. The reduced need for extensive life support resources and supplies could also lead to more streamlined mission planning and execution. 3. Collaborative efforts with industry partners. The successful development of the NTP system is a result of collaboration between NASA and private industry partners, particularly General Atomics Electromagnetic Systems (GAEMS) and Space Nuclear Power Corporation (SpaceNukes). This partnership is crucial in leveraging expertise and resources to advance nuclear propulsion technology. The collaboration demonstrates a multifaceted approach to overcoming the challenges of deep space exploration, emphasizing the importance of private sector involvement in achieving ambitious space exploration goals. 4. Future implications for space exploration. The implications of successful NTP technology extend beyond Mars missions. Faster propulsion systems could facilitate more ambitious explorations of the outer planets and support establishing sustainable human habitats on the Moon and Mars. The advancements in NTP technology may redefine the landscape of interplanetary travel, making it not only feasible but also efficient. As NASA and its partners continue to refine this technology, it could play a pivotal role in shaping humanity's long-term presence in space, opening new frontiers for exploration and discovery. 1. The Manhattan Project 1942–1946. This was a research and development project during World War II that produced the first nuclear weapons. The project involved collaboration between scientists and the military, resulting in significant technological advancements in nuclear physics and engineering. The successful testing of the atomic bomb in 1945 fundamentally changed warfare and international relations, similar to how NASA's NTP technology has the potential to revolutionize space travel. 2. Project Orion 1955–1965. This was a study of a spacecraft intended to be directly propelled by nuclear explosions. The concept involved detonating nuclear bombs behind the spacecraft to propel it forward, aiming to achieve speeds that would allow for interplanetary travel. Despite never advancing to a flight-ready stage, Project Orion represented an early attempt to harness nuclear technology for space exploration, paralleling NASA's current efforts with NTP systems to utilize nuclear energy for propulsion. 3. NERVA nuclear engine for rocket vehicle application 1955–1972. The NERVA program developed a nuclear thermal rocket engine that successfully conducted ground tests. It aimed to enhance the efficiency and capabilities of space travel, specifically for missions to Mars and beyond. Although NERVA was ultimately discontinued, it laid the groundwork for modern nuclear propulsion concepts. Much like NASA's current NTP technology aims to build upon previous efforts to achieve faster, safer human missions to Mars. Future outlook. Predictions for NASA's revolutionary nuclear space engine. NASA's groundbreaking advancements in nuclear thermal propulsion (NTP) technology are set to revolutionize human space exploration, particularly missions to Mars. As testing progresses and partnerships strengthen, several predictions can be made regarding the future of NTP systems and their implications for interplanetary travel. 1. Accelerated human missions to Mars. With the potential to reduce travel time to Mars from 6 months to just 45 days, NTP technology could lead to the first human missions to the Red Planet within the next decade. NASA is expected to finalize its design and begin operational testing of the NTP system by the late 2020s. This accelerated timeline may allow for the first crewed Mars mission as early as the 2030s, significantly advancing humanity's presence beyond Earth. 2. Enhanced safety for astronauts. The reduction in travel time translates directly into enhanced safety for astronauts. Shorter missions mean decreased exposure to cosmic radiation and reduced risks associated with long-duration spaceflight, such as medical emergencies or equipment failures. Future missions will likely incorporate robust health monitoring systems and advanced life support technologies, ensuring astronauts remain healthy during their journey. 3. Broader applications beyond Mars. While the immediate focus is on Mars, NTP technology's implications extend far beyond. By enabling faster travel to Mars, NTP could also facilitate missions to the outer planets such as Jupiter and Saturn, and even support the establishment of human habitats on these celestial bodies. The technology could also play a crucial role in future exploration of asteroids and comets, expanding our understanding of the solar system. 4. Commercial opportunities in space exploration. The successful implementation of NTP systems is likely to spur commercial interest in space exploration and transportation. Private companies may leverage this technology for commercial missions, satellite deployment, and space tourism. This could lead to the development of a more robust space economy, with NTP as a cornerstone of commercial interplanetary travel. 5. Strengthen international collaboration. As nations recognize the potential of NTP technology, international collaboration may become more prevalent. Countries with advanced space programs could partner with NASA to share knowledge, technology, and resources. This collaboration may enhance global efforts towards sustainable exploration and habitation of other planets, promoting peace and cooperation in space endeavors. 6. Technological advancements and spin-offs. The development of nuclear thermal propulsion will drive technological advancements across various fields, including materials science, robotics, and environmental engineering. Innovations stemming from NTP research could have terrestrial applications benefiting sectors such as energy production, transportation, and safety engineering. 7. Public interest and support for space exploration. As NASA continues to make strides in nuclear propulsion technology, public interest in space exploration is likely to grow. Successful milestones in NTP development and subsequent missions to Mars could inspire future generations to pursue careers in STEM fields, fostering a renewed passion for space science and exploration. 8. Addressing environmental concerns. The transition to nuclear propulsion may also prompt discussions about sustainable practices in space exploration. As humanity seeks to establish a presence on other planets, the importance of minimizing environmental impact will become paramount. Future missions may incorporate sustainable technologies and practices, ensuring that space exploration does not exacerbate existing environmental issues on Earth. 9. Increased funding and policy support. With the growing recognition of the importance of NTP technology and its potential applications, government agencies and private entities may increase funding for space exploration initiatives. This financial support will be crucial for the continued development and refinement of NTP systems, facilitating upcoming missions and ensuring the technology is ready for operational use. 10. Ethical considerations and safety protocols. The implementation of nuclear technology in space travel will necessitate the development of stringent safety protocols and ethical guidelines. As the use of nuclear propulsion systems becomes more prevalent, discussions on the safe handling of nuclear materials and the potential risks associated with space travel will be essential. Developing comprehensive safety measures will be critical in gaining public trust and ensuring the responsible use of nuclear technology in exploration. Conclusion: NASA's nuclear thermal propulsion technology represents a transformative step in human space exploration with the potential to reshape our approach to interplanetary travel. As we look to the future, the implications of NTP systems extend beyond Mars missions, promising advancements that will enhance astronaut safety, foster international collaboration, and inspire a new generation of explorers. The next decade will be pivotal in realizing these predictions, paving the way for humanity's future in the cosmos.